So we have seen how to find spanning trees of a simple graph using breadth-first search and depth-first search. Next, we are going to discuss minimum spanning trees, and these are defined in weighted graphs. The minimum spanning tree, or rather a minimum spanning tree of a simple weighted graph, is a spanning tree with a minimum total weight. The idea is still the same. You want to connect every vertex using a tree, but now you would like to include the edges in such a way that the total weight of the spanning tree is minimized. Again, for this, we have a number of algorithms, but in this course, we are going to study the most famous two of them, Prim's algorithm and Kruskal's algorithm. These are very similar to each other, and in Prim's algorithm, both are greedy algorithms, and in Prim's algorithm, you start with an edge with a minimum weight. So you select one of the edges that has the minimum weight across the entire graph and add that to your minimum spanning tree. And in a loop, you select an edge with minimum weight incident to the minimum spanning tree that does not lead to a simple circuit. So among the edges that are incident to the current minimum spanning tree, find the one or find one among the ones that has minimum weight and that does not lead to a simple circuit and add it to the minimum spanning tree. And you repeat this procedure until you have a number of vertices minus one total edges, because that's the number of edges we will see in the minimum spanning tree. Now, this will give you a minimum spanning tree, and this is Prim's algorithm. And when it comes to Kruskal's algorithm, the main difference is in that Prim's algorithm builds the minimum spanning tree by keeping the tree always connected. You see the minimum weight edge incident to the minimum spanning tree is selected at each iteration. But in Kruskal's algorithm, you see, select any edge with minimum weight that does not lead to a simple circuit, add to the minimum spanning tree. So you don't look for incidence. So you just select the edges with minimum weights. They do not have to be incident to the same vertices. So in between iterations, your structure, your running minimum spanning tree, so to speak, may be and may not be a connected graph. But if you repeat this until the expected number of vertices, or rather expected number of edges are included, at the end, what you will have is a connected tree. Now, let's see these in action. Let's look at this simple graph, and we are going to run both algorithms on this. And recall, in Prim's algorithm, you select one of the edges that has minimum weight across the graph. So when you look at the graph, the weights are 1, 2, 3, 4, 5. So the ones with a weight of 1, this one, and this one, I want to select one of them and start there. And this selection, again, it could be random, it could be according to some certain criterion, depends on your implementation. Let's say we select this one. Now, Prim's algorithm requires the tree to be connected all the way through. So I'm going to look at the edges incident to this edge. This one, this one, this one, this one, and this one are the candidates for the next edition. And among them, you see I have 2 and 2 here. The others are 3, 3, and 4. So these are the minimum, and among these, I will select one of them. Again, I can do this randomly. Let's say I select this one. You see, if you select the other one, it might lead to a different minimum spanning tree, and that's the reason I said a spanning tree or a minimum spanning tree. because it may not be unique. And now at this point, the candidates are this one, this one, this, and this. And among these, the minimum cost is this one. So now I don't have any other choice. I will have to select that one to add to my minimum spanning tree. Again, I can select this one, or this one, or this, and this as my next edge to add to my minimum spanning tree. Now, when you look at the weights, I have 3s and 4s. So I will have to select one of the 3s, and let's say I select this one. Okay, again, repeat the iteration. The next candidates are this one, this one, this one, this, and this, because these are the ones incident to my current minimum spanning tree. So when you look at the weights, again, I have 3s and 4s, so I will select one of the 3s, and I have selected this one. Continuing, now I can select this, or this, or this, or this one, or this one, or this one, or this one. Now, when looking at these, I have this 2 as the minimum, so my next addition has to be that one. And again, I'm going to look for the candidates in the next iteration. By the way, I'm going to repeat this 11 times because you see I have 3 times 4, 12 vertices here, which means in my tree, I will have 11 edges. So I'm going to repeat this iteration 11 times. Now I'm at 1, 2, 3, 4, 5, 6. So I'm going to do this 5 times more. Now at this stage, this is a candidate. This is another candidate. This is another one. Now this one is no longer a candidate because it will lead to a simple circuit here. Therefore, I will never able to select this one from this point on. This one is another candidate. This one and this one and this one are candidates. Now I have a 1 here as a candidate, so that's the minimum. Therefore, I will add that one next. And therefore, in the next iteration, these are my candidates, this one and this one, and this one and this one. Among these, I have 3s, 4s, and a 5. So I will have to select one of the 3s as my next addition, and I have selected this one. Okay, so for the next iteration, this is out, and this is also out because it will lead to a cycle here. And this is also out because it will lead to a cycle here. And I can select this one, or this one, this one, or this one. So 3, 4, 3, 5. So I will again select one of the 3s. This one is selected. In the next iteration, this is out, this is out, this is out. So this is a candidate, this is a candidate. This again is out because it will lead to a cycle here. This is a candidate. And since this one has a cost of 1, I will use that one to add. And now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm just going to need another one. And this is out, this is out, this is out, this is out. This one or this one or this one are my candidates. So I will have to select one of the 3. This one is selected. Therefore, this completes my minimum spanning tree. And if you compute the total cost, so 3, 5, 6, 7, 10, 12, 15, 16, 19, 21, and a total of 24 is the cost of the total weight of this minimum spanning tree.